Welcome to another class of intermediate microeconomics. I hope you had a wonderful day today so far, and I hope to help you to have another beautiful 2 hours watching this lecture, although you can also do it in parts. So today's lecture is on game theory and how appropriate we will also derive our real life example from a game that many of us often watch, being soccer. So in soccer, an event that happens now and then is that one of the players needs to kick a penalty. And then the player has to decide whether to kick the penalty left or to the right of the goalkeeper. And this is the action space. So there are two possible actions, kick left or kick right. And the question is, what is the optimal thing for the player to do? Well, most players, they have a preference for left or right because, well, for example, they are right-footed, so they feel that they can kick more precisely the ball into the corner if they aim right. Well, would that be a reason to always kick the ball to the right of the goalkeeper? No, because the goalkeeper will anticipate that. He will know which player he faces and what the preference of the player is. And if the player is known for always kicking the ball to the right, then he will also dive to the right and stop the penalty. So the player will not be successful. So it's not optimal for the player in general to what economists call use a pure strategy, to kick the ball always in the same corner of the net. So to always choose the same action. So it's better for the player, in order not to be fully predictable, to mix between aiming left and aiming right. Now, what we're going to do today is to study that type of games and to arrive at a conclusion to derive what is the optimal mixing between the possible actions. So in this case, the player has two actions. For example, he may prefer to choose to kick the ball to the right because he's right-footed and has more precision, but he cannot always kick to the right, so he will mix. With a certain probability he will kick to the left, with a certain probability to the right. He may kick the ball a little bit more to the right than to the left on average, and we're going to find out, okay, what is then the optimal mixing probability of a player. And this example that is shown here is from a penalty kick in a game between Hamburg and Freiburg a couple of years ago. Actually, the neat thing is that the Dutch player Rafael van der Vaart helps the goalkeeper here by pointing out in which direction the player will kick. And that helped because the goalkeeper dived into this direction and the penalty was stopped. So this is from a real-life game, and economists, they study penalty kicks also professionally. So Palacios Huerta wrote a study on the strategy of kicking penalties, and for that study he analyzed 1,417 penalty kicks that were kicked in the major European leagues, such as the Spanish league, the league in Italy and in England. Now, I think this is a nice advertisement for being interested in doing economic research because, well, doing that type of research will allow you to spend a lot of time watching penalty kicks and to analyze the data. But what did he find? Well, he of these 1,417 penalty kicks, he selected a player that kicked at least 30 penalties. And here you see a number of them listed. So kicker 1 is found to aim left in 32% of the cases and to aim right in 68% of the cases. So he might have a preference for kicking right, but he does not exclusively kick right. And then what Palacios Huerta studies is, okay, how successful is this player when he kicks left and when he kicks right? And it turns out that his scoring rate is identical in both cases. So if he kicks right, he scores 9 out of 10 times. If he kicks left, he also scores 9 out of 10 times. So the payoff of kicking left and kicking right is exactly identical. And this is what we will see in general. If players play a mixed strategy, then the payoff of playing each of the pure strategies is identical in equilibrium. So what he finds is that this penalty kicker follows a Nash equilibrium strategy. When he kicks right, he has more precision there, but it's not as surprising to the goalkeeper. So he scored 9 out of 10 times. If he kicks left, which he does less often, probably he is not as precise to kick the ball into the corner, but there's a surprise effect there because the goalkeeper expects it less that the player will kick left, and he will also score 9 out of 10 times. Now, this not only holds for kicker 1, but the convincing evidence in this study is that if you analyze the different kickers from 1 to 10 as listed here, they mix all with different probabilities. So kicker 5 does an equal mixing between left and right. Kicker 6 has really more often kicks to the right than to the left. But if you look at the scoring rate of the individual players, then you will see that for each of the actions, the scoring rate is almost identical. So you can run a statistical test and you find p-values, and the p-values are quite high. They're never below 5%, meaning that these differences are never statistically significant. So now I hope that you will join me for the rest of the lecture and not start watching soccer saying, okay, this is a nice idea, that's what I should do, watch soccer. Please first continue with the lecture today. Because what we're going to do is we're going to look at games, and we are going to look at different strategies, pure strategies where a player chooses one action with certainty, with probability 1, and mixed strategies where players randomly select from several possible actions, so kicking left or kicking right. And the pure strategies you've already known from previous courses, and the mixed strategies is something that is new to you, or to most of you. So a Nash equilibrium in pure strategies is defined as follows. Suppose that we have a row player and a column player, and the row player's actions are denoted R1 to Rn, and the column player's actions are denoted C1 to Cm. And then we define payoffs. So we know that in the form of utility, so with a U, sometimes it's also denoted with a pi, because that is representing kind of a profit or payoff. And the payoff to player row associated when row plays action Ri and column plays action Cj is given by this functional form over here, which is a function of the actions of both players. So your payoff not only depends on what you do, but also on what the opponent does. And that's what it makes a game. And the same for the column player. Now, usually with 2 players and a limited number of actions, we can represent this game in a matrix form where the payoffs are denoted as entries into the matrix. So this is the famous Battle of the Sexes game. And we have 2 players, a column player and a row player. And the question that they need to decide upon is where to spend the holiday. And these 2 players, they like each other, so they prefer to go on holiday together, but they have their own individual preferences for where to spend the holiday. So the row player is rather in Italy than in Sweden, and the column player prefers Sweden over Italy. So this means that if they end up in Italy, so they both decide to go to Italy, then the row player will get a positive payoff of 2 and the column player a payoff of 1. And if they both decide to go to Sweden, then it's the other way around. The row player gets 1 and the column player gets 2. And in these matrices, always the payoff to the row player is the first entry and the payoff to the column player is the second entry. But then if one of them decides to go to Italy and the other one decides to go to Sweden, then they do not end up together, which is bad for both of them. And in those cases, the payoff of each is equal to 0. So what is the Nash equilibrium in this game? Or what are the Nash equilibria? Now this is something you know as far as we look at pure strategies. So the formal definition of a Nash equilibrium is that it's a pair of strategies such that none of the players has an incentive to deviate from his or her strategy given the strategy of the other players. So formally, the pair of strategies R star, C star is a Nash equilibrium if for both players it holds that the payoff of playing this pair of strategies is at least equal than the payoff if, given what the other player does, one of the players will deviate. So the row player cannot attain a higher payoff if he chooses instead of the equilibrium strategy R star, the action RY, given that the column player plays C star. And the same holds for the column player. Given that the row player plays R star, there's no way that the column player can do better by playing another strategy CJ than C star. So this is the definition of a Nash equilibrium. So no player wants to deviate unilaterally given the choice of the others. And in this case we have so-called pure strategies. So strategies that are played with certainty, with probability 1. So in our game, the Battle of the Sexes game, there are Nash equilibria. And so what are the Nash equilibria of this game? Well, Italy and Sweden are the two Nash equilibria of this game. So you can see it as follows. Given that the column player decides to go to Italy, it's optimal for the row player to choose Italy as well, because in that case he receives a payoff of 2, which is higher than the payoff of 0 when he would go to Sweden. Identically, for the column player, given that the row player decides to go to Italy, we are in this row over here, and you can easily see that in that case, given that the row player chooses Italy, it's optimal for the column player to choose Italy as well, because then the column player's payoff will be 1 instead of 0. And you can also check yourself that Sweden is also a Nash equilibrium in pure strategies of this game. So this you already knew from your previous microeconomics courses. And now we're going to do something that is new. We're going to consider mixed strategies. So like in the example with the penalty kicker, are there additional equilibria where the two players mix between playing Italy and Sweden? Now, in order to find a mixed strategy equilibrium, we first need to define what we look for. So a mixed strategy for a player row is a probability distribution, because now he mixes between the two. And this probability distribution, because we only have two actions, we can represent it by only one number, PR. And PR is the probability with which the row player will play Italy. And then with probability 1 minus PR, he will choose the other action, Sweden. So what the row player now must do, we leave the realm of the pure strategies. So it's no longer between choosing Italy or Sweden with certainty, but the row player has to select PR, the probability with which he will play Italy. So that's the decision variable. And the same for the column player. So the column player must select a probability PC with which the column player will play Italy. Note that this is the same example as in the book, example 8.3, but the notation is slightly different because in the book the notation H and W is used instead of PC and PR, but I prefer the notation that we use here. Okay, so now deriving the Nash equilibria in mixed strategies in this game. And the fundamental idea of the Nash equilibrium remains the same. So if a pair of strategies is equilibrium strategy in mixed strategies, then it must hold that the choice of each of the player is optimal given what the other player does. So for the row player, his choice of PR must be optimal given that the column player chooses PC, and for the column player, choosing PC must be optimal to her given that the row player chooses PR. And note that here we assume that each player holds correct beliefs about the opponent's behavior. So we impose a rational expectations assumption in order to close the model. So if the row player decides to play Italy with probability PR, then we assume that the column player has the correct belief that the row player will choose Italy with probability PR. In the next 10 to 15 minutes, I will show you two methods to solve for the equilibria in mixed strategies, how to find them. And there's a complicated or a little bit more complicated method, and there's a easier method. And I will start with the more complicated method and save the best for last. So why, if we have an easy method, also to discuss a more complicated method? Well, the reason is that the complicated method starts from first principles. So it starts from the optimization problem that the agents are trying to solve. So let's consider the row player. So he wants to maximize his utility, and given that we're in a situation where we allow for mixed strategies, we talk about the expected utility because it depends on the probability with which each of the players chooses a certain action. And for the row player, the expected utility is as follows. So he chooses to play Italy with a certain probability, PR. And in case that he plays Italy, his payoff will be 2 in case of the row or the column player also plays Italy, which happens with probability PC. And he will receive a payoff of 0 if the column player decides to go for Sweden, which happens with probability 1 minus PC. So this is the expected payoff of the row player playing Italy times the probability with which he will play Italy in equilibrium. Then if he doesn't play Italy, he will play Sweden, and in equilibrium that we look for, he will do so with probability 1 minus PR, in which case he will receive a payoff of 0 if the column player decides to play Italy, which happens with probability PC, and a payoff of 1 if the column player decides to play Sweden as well, which happens with probability 1 minus PC. Fortunately, we can simplify this expression because we have zeros. And if you multiply something with 0, nothing is left. So that is what we will do in the next step. And you please recognize then when trying to find the optimal probability to play Italy, so to find the probability PR, this probability needs to be between 0 and 1 because it is a probability. So that's the constraint on the probability. And now we simplify the objective function, so the expected utility. And And we can do so as follows. Well, these terms, they drop out. The other terms, they can be simplified. And we are left with an expression PR times, within parentheses, 3PC minus 1 plus 1 minus PC. And the reason for writing it in this particular form is that now we have only one term with the decision variable of the role player, PR, left. And then we have something that is a function of PC only. And what does that give us? Well, we want to maximize this entire expression by choosing a probability PR correct. And you can see that, well, whether we want to choose PR as large as possible or as small as possible very much depends on the term within parentheses. If this term is positive, then it pays off to choose PR as large as possible. Well, okay, we are bound to not setting it higher than 1, so then we will equate it to 1. If, in contrast, this term is negative, then the player will maximize his utility by choosing PR as small as possible, and you cannot go below 0, so you will set it to 0. That is the mechanism. So it depends on the probability with which the column player mixes between Italy and Sweden. If PC is larger than 1/3, then this thing is positive. So the chance that the column player chooses Italy is sufficiently large. Well, then for the role player, it's also optimal to choose Italy. If instead this value is smaller than 1/3, then probability that the column player chooses Italy is rather low, and it's better for the role player not to mix, but to go for Sweden for certain. So PR identical to 0. And then there's the borderline case where the column player chooses Italy with probability 1/3. Well, then this term within parentheses is identical to 0. It vanishes. So the expected utility of the role player is then 1 minus PC, and PC is equal to 1/3. So the expected utility is then 2/3 for any value of PR. So given that the column player mixes and chooses Italy with probability 1/3, then any value of PR is optimal for the role player, because all of these values will give him an utility of 2/3. So Rowe mixes over his two pure strategies, and now we can do the same for the column player. So we have the similar problem. The objective function of the column player reads as follows. The column player maximizes this expected utility function subject to a similar constraint on the probability. Again, we can simplify, please check it yourself, and we get this expression over here. So for the column player, so that is the person who rather goes to Sweden than to Italy, but still the column player will decide to go to Italy for sure if the role player has a sufficiently high probability of choosing Italy. When it's lower than 2/3, then it's optimal for the column player to choose Sweden. And then again, we have a borderline probability of 2/3. So when the role player chooses Italy with probability 2/3 and Sweden with probability 1/3, then any choice of PC is optimal for the column player. It doesn't matter because this first term has vanished. And one of the particular values that the column player could choose, because in that situation all probabilities, all PCs give the same expected payoff. So one of the specific values that she could choose is the value 1/3. Well, and then we go back. Given that the column player mixes between Italy and Sweden with probability 1/3 for Italy, then for the role player, any value of PR is optimal. So for example, he could choose a PR equal to 2/3, because if he chooses PR equal to 2/3, then PC is 1/3 is also an optimal choice for the column player. So now we have found the mixed strategy equilibrium. Both players mix. The column player mixes with probability 1/3 choosing Italy, and the row player chooses Italy with probability 2/3. So combining the results, this is what we find. If the row player chooses Italy with probability 0, it's optimal for the column player to choose Italy also with probability 0, and vice versa. If the column player chooses Italy with probability 0, so certainly the column player decides for Sweden, then it's optimal for the row player also to decide for Sweden. So this is the first equilibrium in pure strategies, and it's consistent with this one. If PR is smaller than 2/3, so say 0, then it's optimal for column to play PC 0 as well, and vice versa. If the row player chooses or the column player chooses PC is 0, then for the row player it's optimal to choose PR is 0. That is the first equilibrium in pure strategies. So we already knew it from the start, but it now also follows from our solution method where we allow for mixed strategies. Also the pure strategy equilibria, they roll out automatically. That also holds for the second equilibrium in pure strategies. But now we've allowed for mixed strategies. We find one additional Nash equilibrium. A Nash equilibrium in mixed strategies where the row player chooses Italy with probability 2/3 and the column player with probability 1/3. And you can verify that both players in this mixed strategy equilibrium obtain a payoff of 2/3. So, for example, for the row player, we can plug in the values. So this is just plugging in the values in this expression over here. PR equal to 2/3, PC equal to 1/3, and solving it, you get a payoff of 2/3. So here we are using expected utility. We choose our probabilities PR and PC such that we maximize our own expected utility. And note that each of the players would prefer either of the pure strategy equilibria. So it's not that the mixed strategy equilibrium gives you a higher payoff as a player than playing the pure strategy equilibrium, because playing any of these two pure strategy equilibria would give one of the players a payoff of 1, the player that ends up not in the country of choice but with the partner of choice, and it would give a payoff of 2 to the person who ends up in the country of choice with the partner of choice. Whereas here, both players would only get a payoff of 2/3. So either player would, or each player would prefer either of the two strategies or equilibria in pure strategies. We can also show it graphically. So this is the best response function that you know from previous coursework. But now we don't have the different actions on the x and the y-axis, but we have the probability on the x-axis and the y-axis. So this is the notation from the book, but this is the probability with which the row player mixes between Italy and Sweden. It runs from 0 to 1. And this is the probability with which the column player mixes between Italy and Sweden. So we observe that 0, 0 is an equilibrium, because if we map the best response function, say, of the row player, so that's the one over here. This is the best response function of the row player. If the column player chooses Italy with probability 0, it's optimal for the row player to choose Italy with probability 0 as well. It remains optimal for the row player to choose PR equal to 0 as long as PC is smaller than 1/3. When PC is exactly equal to 1/3, the row player is indifferent between choosing Italy, choosing Sweden, or anything in between. So we have a horizontal line on the best response function for the row player. And as soon as the probability with which the column player chooses Italy exceeds 1/3, then the best response of the row player is to choose Italy for certain. So with probability 1. So that is the last vertical part of the best response function of the row player. Now you can also draw the best response function of the column player that goes along the same lines. Well, same mechanism, different lines that we obtain. And combining the two best response functions, we easily find all the equilibria by looking at the points where the two best response functions intersect. And they do so at the point 0, 0. So that's one of our equilibria in pure strategies. The second equilibrium in pure strategies is the point where both choose Sweden with probability 1 or Italy with probability 1. And then here we have the third equilibrium in mixed strategies, where the row player chooses Italy with probability 2/3 and the column player with probability 1/3. So finding the Nash equilibria by looking at the points where the best response functions intersect also works with a situation where we look for mixed strategy equilibria. As promised, also an easier solution method. And now you are ready for the easier solution method because, well, you went through the pains of the more difficult one. So we start with the observation that if a mixed strategy is a best response, then each of the pure strategies involved in the mix, so in our example both Italy and Sweden, must itself be a best response. So in particular, each must yield the same expected payoff. So here we have a mixed strategy equilibrium. It involves the two pure strategies, Italy and Sweden. So given that the column player mixes between Italy and Sweden and chooses Italy with probability 1/3, then the row player mixes between Italy and Sweden, and he mixes between the two. This implies that he's indifferent between choosing either Italy or Sweden for sure, between choosing Italy for sure, or any combination of the two. And because he's indifferent, it means that his expected utility of playing Italy for sure, Sweden for sure, against a column player who mixes with probability 1/3, it means that each of these two strategies must give him the same payoff. And we're going to utilize that. So Row's expected payoff of playing the pure strategy Italy against the column player who mixes between Italy and Sweden in some proportion is identical to, well, the row player now plays Italy for certain. So that will give him a payoff of 2 if the column player plays Italy as well, which happens with probability PC. And he will receive a payoff of 0 if the column player chooses Sweden, which happens with probability P minus 1 minus PC. So simplifying, if the row player chooses Italy with certainty, then his expected payoff is equal to 2 times PC. Now, what about the other pure strategy going to Sweden? If the row player plays that against the column player mixing between the two, well, if he decides on Sweden, his payoff will be 0 if the column player chooses Italy, which happens with probability PC, and the payoff will be 1 if the column player chooses Sweden as well, which happens with probability 1 minus PC. So the expected payoff of choosing Sweden against this mixing column player is 1 minus PC. In the mixed strategy equilibrium, the role player is indifferent between playing either of these pure strategies that is involved in the mix. So for the pair of strategies to be a mixed strategy equilibrium, it needs to hold that the expected payoff when playing Italy is the same as the expected payoff of playing Sweden. So we can equate these two and solve for PC. Because noted that so far we said, okay, we want to find a mixed strategy equilibrium, and we know that if we have a mixed strategy equilibrium, then the role player mixes between two of his pure strategies, but he must be indifferent between playing either. But we did not yet specify the value of PC. And now we're going to equate these two, because that needs to hold in equilibrium, and we solve for the value of PC. Now that's easy. So PC needs to be equal to 1 minus PC. Solving, we get that PC is equal to 1/3. And this is no surprise because it's exactly the same value that we found when using the more complicated method. And the same, in the same way, we can also find the equilibrium value with which the role player mixes in the mixed strategy equilibrium. So we use the fact that, so if rho is mixing on both our pure strategies in the Nash equilibrium, then both must yield the same expected payoff, in which case column must be mixing with weights 1/3, 2/3. And we use the fact that in this equilibrium, rho must be indifferent between the two strategies that are involved in her mix. And in the same way, we can find the equilibrium value for the rho player, and we will arrive at PR is equal to 2/3, just as in the example before. You can check it yourself. So, well, let's check whether this mixed strategy profile 2/3, 1/3 is really a Nash equilibrium. Does it satisfy our definition of a Nash equilibrium? Well, in order to be a Nash equilibrium, none of the players need to have an incentive to deviate given the strategy by the other player. So, and it's easy to see that this holds in this particular case because we have constructed the mixed strategy equilibrium exactly such that given how column mixes, given PC, the role player is indifferent between either of his two pure strategies involved in the mix. And being indifferent means that they need to lead to the same expected payoff in equilibrium. And the same argument applies to the column player. Okay, so to summarize, in a mixed strategy, a player randomizes only over those actions among which he or she is indifferent. And if you consider one player's indifference condition, then you can use that to pin down, to determine the other player's mixed strategy. So, final note, John Nash proved the existence of a Nash equilibrium in all finite games, meaning games where each player has a finite number of possible actions. And this existence theorem by John Nash doesn't guarantee that all games have an equilibrium in pure strategies. So if you have rock, paper, scissors, that's, for example, a game that doesn't have an equilibrium in pure strategies. So what the existence theorem says is that each finite game has a Nash equilibrium. So if the game doesn't have a Nash equilibrium in pure strategies, then it must have an equilibrium in mixed strategies. And it also holds for rock, paper, scissors. So you can maybe already guess what is the equilibrium in that game in mixed strategies. And well, you can check whether your hunch is right by doing the formal derivation. And that completes the first part of this lecture. Then there are 3 sections in the book, the content of which are part of this course, but which we do not discuss extensively in this course, because you know the content in a different form from the previous course, Microeconomics 2. And these 3 sections are 8.6, which deals with continuous actions. So what if you, as a player, you do not choose between left or right, or you have 10 possible actions, but you have a continuum of choices. So you have a continuous action space, for example, if you need to choose a price, or as a firm when you need to choose a quantity. Section 8.7 deals with sequential games. So what if players do not choose simultaneously at the same time, but the action of player 1 is followed by the action of player 2. And player 2, in deciding, can take into account what he or she has observed player 1 doing. And then in section 8.8, repeated games is a topic. So what if players do not meet each other only once to play a game, but they play the same game repeatedly with each other? But as said, I don't discuss these sections explicitly here. I will continue with 8.9, which is about a new topic, games of incomplete information. And although this is all very logical, it may not be straightforward if you first deal with this topic. So what is the situation? Some players in the game now have information that other players do not have. And the players that do not have the full information, they will try to use what they do know to make any inferences about what they do not know. So this is quite secretive language, but I will become much clearer in what follows. So what we will do is quite simple. We focus on simple games with 2 players, and we assume that player 1 has private information, something that player 2 doesn't know, and all that player 2 knows is also known by player 1. And private information into game theory is modeled by introducing player types. So, and there are 2 flavors. So in section 8.10, and that's the part that we are going to discuss in this course, is when both players move simultaneously, but one of them has private information. And then section 8.11 of the book deals with so-called signaling games, where the player which has more information moves first. So, and that's signaling games are covered in the Master of Economics. So if you're interested in that, you still need to wait a bit. But I can assure you that 8.10, games of incomplete information where both players move at the same time, is already very interesting and leads to new insights. So the setup is as follows. We have a 2-player game. They play at the same time. And player 1 has private information and player 2 has not. And we model the private information by introducing player types. So player 1 can be a number of possible types T, and he or she knows his or her own type and also can condition on it in making choices. And player 2 is uncertain about the type of player 1, but must decide which strategy or action to choose based on her beliefs on the type of player 1. So this game begins at a chance mode, meaning that nature will decide the type of player 1. So nature draws a type from a set of possible types T1 till, say, Tk. And the probability that player 1 is of a certain type is information that's known also to player 2. So the probability that player 1 is of type TK is PK. Player 1 observes the type that is drawn, and player 2 does not observe this, but does observe the probabilities. So this is also the situation where I, as an instructor, I need to find out whether students cheat. I don't know, I don't observe whether a student is of the cheating type or not, but I do have some idea of the probabilities, saying, for example, that maybe 10% of all students is of the cheating type and 90% is of the sound non-cheating type. I must confess that I don't know, don't even know the exact probabilities. I'm even in the dark about that. I don't know whether it's higher than 10% or lower than 10%. I hope it's as small as possible. Okay, but that aside, player 1 observes the type before he will move, so he can condition his strategy on his type. So we denote the strategy of player 1 as a function of his type as S1, 2. And player 2 strategies is an unconditional strategies. So, and the type of player 1 may affect the payoff of player 2 in two ways. In a direct way, because he's of a certain type, and also in an indirect way, being that, well, being of a certain type influences the strategy of player 1, and that in turn impacts the payoff to player 2. Let's do a simple example. So we have two players, and now player 1 is of type T is 6 with probability 1/2, and type T is 0 with the other half probability. Meaning that the payoff matrix, as we know it, player 1 knows the full payoff matrix, but player 2 is in the dark about the exact value of the T over here. So with probability 1/2, T is equal to 6. With probability 1/2, it is equal to 0. And player 1 knows the value of T. So yeah, we can write this game instead of in matrix form also in extensive form. So that looks as follows. First, we have this draw from nature, drawing the type of player 1. Then this is the decision nodes of player 1. Player 1 can condition his or her strategy on his or her type because he observes the type that is drawn by nature. But player 2, at the decision node of player 2, we have this dotted area around it because player 2 does not know whether he at which node he is when making the decision for left or right, because he doesn't know the realization of the type of player 1. So all four player 2's decision nodes are in the same information set, because she does not observe player's 1 type before she has to decide what to do. And, well, what we learned in the course is to find an equilibrium, a Nash equilibrium, and the type of equilibrium that we need to find in games of incomplete information are called Bayesian Nash equilibrium. And again, the equilibrium requires that for player 1, the strategy that he chooses in equilibrium is the best response to for each and every one of his types. So he needs to decide, okay, if I'm of type 0, what's the optimal thing to do? And if I'm of type T is 6, what is the optimal thing for me to do? And for player 2, player 2 maximizes an expected payoff because he knows the probabilities that player 1 is of a certain type, but he doesn't know exactly which type player 1 is in a given instance. So she needs to take the expectation with respect to the belief she has about player 1's type. And that brings us then to the formal definition of a Bayesian-Nash equilibrium. So that's the solution concept that we apply here. And the strategy profile S1T star S2 star, where we observe that the strategy of player 1 is a function of, is conditioned upon player 1's type. This strategy profile is a Bayesian-Nash equilibrium pair of profiles if it holds that for all types of player 1, the utility that the player 1 derives, of the player 1 of a certain type derives from playing that particular strategy is at least equal to the payoff that he would receive if he would play any other strategy. And for player 2 takes an expectation and maximizes an expected payoff. So the equilibrium strategy of player 2 must satisfy the condition that the expected utility payoff of playing that strategy is at least equal to the expected utility that she would derive if she would play any other of her feasible strategies. So, and these other feasible strategies are denoted as 2 prime. So again, the solution concept is very much in line to the concept that we saw before with the mixed strategy equilibria, except that now one of the players has private information about his type. Okay, so let's return to our two-player example where both have 2 possible actions and player 1 can be 1 out of 2 types. So player 1 can be of type T is 0 or T is 6, and each of these types is drawn with probability 1/2. And player 1 knows exactly which matrix he faces. He knows, okay, I'm of type T is 0, so this is the matrix that we face when we need to make a choice. If he observes that he is of type T is 6, then he knows that this is the relevant payoff matrix of the game. And you can see that, well, if player 1 is of type T is 0, then it's optimal for him to play D down always. Because that's the dominant strategy in this case. 2 is more than 0, 2 is more than 0. So independent of what player 2 will decide, it's optimal for player 1 to play down if he's of type T is 0. If he is of type T is 6, well, then his optimal response to player 2 playing left is to play up, because that gives a payoff of 6 instead of 2. But if player 2 decides to play right, then it's the optimal response of player 1 is to play down, because 2 is more than 0. This leaves us with 2 possible candidates for Bayesian-Nash equilibrium in pure strategies. And note that I've underlined pure here because we're first going to look at equilibrium strategies where none of the players mixes between actions. So player 1, conditional on his type, will play one action with probability 1, and player 2 in such an equilibrium will also choose an action with probability 1. So the first candidate is where player 1 plays down if T is 0, because that's the dominant strategy when T is 0, and he plays up when he's of type T is 6. And player 2 plays L. Now it's clear that given that player 2 plays L, it is indeed optimal for player 1 to choose the actions exactly like this. To go for down if he's of type 0, and if he's of type 6, then it's optimal for him to play up, because 6 is more than 2. However, what about player 2? Is it really optimal to play L given that player 1 plays this strategy? Well, we need to look at the expected payoff of player 2. And if player 2 will play left, then his expected payoff, given what player 1 does, is he receives a payoff of 0 if player 1 turns out to be of type 0, which happens with probability 1 minus P6, because in that case, player 1 will play down and player 2 will be left with a payoff of 0. With probability P6, player 1 is of type T is 6, in which case player 1 will play up. And if player 1 plays up, the payoff to player 2 will be equal to 2 if player 2 plays left. So the expected payoff to player 2 in this case is 1 if P6 is equal to 1/2, as we have assumed. So could player 2 do any better? So is this really a Nash equilibrium strategy of player 2, or can he benefit by unilaterally deviating? Now, he has only 2 actions, so if he doesn't play L, the only way that he can deviate is to play right. Let's compute the expected payoff of player 2 if he plays right, given that player 1 strategy is still unchanged. Well, in that case, he would receive a payoff of 4 if player 1 happens to be of type T is 0, which happens with probability 1 minus P6, because in that case, player 1 plays down, player 2 plays right, and the payoff to player 2 is equal to 4. However, if player 1 is of type T is 6, which happens with probability P6, then the payoff to player 2 is 0, because then player 1 will play up. Well, if player 1 plays up, then the payoff to player 2 of playing right is 0. And the expected payoff, if we again assume that P6 is equal to 1/2, is equal to 2. And what we observe is player 2 playing L, given the strategy of player 1, is not optimal here. He can do better by deviating to playing right, because the expected payoff of playing right is more than the expected payoff of playing left. So this candidate is ruled out as a Bayesian Nash equilibrium. However, we fortunately have a second candidate. And the second candidate is where player 1 plays down if he is of type T0, because that's the dominant strategy to player 1 in that case, and where he also plays down if he is of type T is 6. And player 2 plays right. And this is a Bayesian Nash equilibrium. It's easy to see because, well, player 1 now plays down always. And then, well, for player 2, it's optimal to play right. Because, well, if player 1 plays down always, then player 2 gets 4 if he plays right, if player 1 is of type T is 0. And if player 1 is of type T is 6, then playing right also gives a payoff of 6 instead of 0. So player 2 cannot do any better than playing right. And also, given that player 2 plays right, it's always optimal for player 1 to play down, because 2 is more than 0, 2 is more than 0. So this is a Bayesian Nash equilibrium of this game. And then we can ask the question, okay, but for which values of the probability that player 1 is of type T is 6 is our first candidate also a Bayesian Nash equilibrium? And that's a question for you to answer. And you know that in order for this one to be a Bayesian Nash equilibrium, so why did it fail to be a Bayesian Nash equilibrium for P is equal to 1/2? Well, the reason was that at P is 1/2, the expected payoff of a deviation for player 2 exceeded the payoff of sticking to the agreement. So what we need to have is that this expression over here is at least equal to this expression over here. So we can equate the two, solve for P6, and we get an answer to our question. And the answer to our question is if P6 is at least equal to 2/3, then candidate number 1 is a Bayesian equilibrium of our game. So another way to show this is the way it's done in the book. So we have two possible equilibria. So player 2 has only two options, left or right, and player 1 has the options up and down, but in addition can also condition on the type. So he has 4 flavors. He can go for up always, he can go for down always, and he can decide to go for up if he's of type T is 0, down if he's of type T is 6, or down if he's of type T is 0, and up if he's of type T is 6. And we can rule this out because up is never the best thing for player 1 to do if he's of type T is 0, because then playing down is a dominant strategy. So these are in gray. We don't have to consider them. And we are left with the 2 over here. Now we can easily see that given that this is the strategy of player 1, it's optimal for player 2 to choose right. And so these are the expected payoffs to player 2. And given that player 1 follows this strategy, it's only optimal for player 2 to choose left if 2 times P6 exceeds the value 4 minus 1 minus P6. So it's the same thing as what we derived here, but that in the form of a table as is presented in the book as well. And now the most difficult question of this lecture, and it may be on the top of your mind right now, are there also Bayesian Nash equilibria in mixed strategies? So equilibria where one player has private information and one or both players mix over their possible actions. It's a great question, and the answer to the question is yes. And we're going to find them. So we will introduce a different solution concept, and this solution concept makes use of strategic form games. So we know them by G star. And in the strategic form games, each type of a player is presented as a separate player. So instead of having 2 players, we now have 3 players because each type of player 1 will be represented by a separate player. And a Bayesian Nash equilibrium of a game of incomplete information is a Nash equilibrium of the associate strategic form game. So notice that we here fiddled in the concept of strategic form games into our definition of a Bayesian Nash equilibrium, because now we consider Bayesian Nash equilibria in mixed strategies. So how does it work? We continue with our example that we just considered. So we have now 3 players. Player 2, and importantly in the way that we are going about it is that the choice by player 2 will determine the payoff matrix. And the types of player 1, so either type T is 0 or type T is 6, will determine the rows and the columns. So, and we will do the general case. So we are agnostic about the probability with which player 1 is of type T is 6. We say, okay, player 1 is of type T is 6 with probability P. And this is what I mean by saying that the choice of player 2 determines the payoff matrix. So we have 2 possible choices. Suppose now that player 2 plays left, then we have the payoff matrix that is given here, where the rows and the columns are determined by player 1 being of type T is 0 or player 1 being of type T is 6. Now, so let's go through a number of these entries. If player 2 plays L, then we are here. If player 1 is of type T is 6, then player 1 will get a payoff of 6 if player 1 then plays up. If this player 1 plays down, he will receive a payoff of 2. If player 1 is of type T is 0, he plays up and player 2 plays L, then the payoff to that player will be equal to 0. And if he's of player type 0 and he plays up, so in player 1 is of type 0, but that doesn't really matter. So then his payoff is also equal to 0. And to player 2, if player 2 plays left, then the payoff is equal to 2 if player 1 is of type T is 0 and plays up. And also if player 1 is of type is 0 and plays up. And important is what happens here. So if player 1 of type T is 0 plays down, but player 1 of type T is 6 plays up, what is then the expected payoff to player 2 of playing L? Well, his payoff is equal to 2 if he meets player 1, because player 1 will play up, and that happens with probability P, because player 1 is of type T is 6 with probability P. If it happens that he meets player 1 being of type T is 0, well, then we know from this entry that that type will play down. The probability that he meets that type is 1 minus P. And in that case, he will get a payoff of 0. So 1 minus P times 0 is 0. So the expected payoff of player 2 playing L, given that player 1 of type 0 plays D and player 1 of type T is 6 plays up, is identical to the probability that player 1 is of type T is 6, in which case player 2 will receive a payoff of 2. Now, for example, this one is easy. If player 1 plays down always, either when he is of type T is 6 or type T is 0, then the payoff of player 2 of playing L will always be 0. And then there's a second matrix, which is conditioned on player 2 playing right. So let's do, now for example, this entry over here. If player 2 plays right, and player 1 plays down if he's of type T is 0, then the payoff to player 2 will be equal to 4. So the expected payoff is 4 times the probability that player 1 is of type T is 0, which is identical to 1 minus P. At this entry, player 1, if he's of type T is 6, will play up. Well, if player 1 plays up, then the payoff to player 2 of playing right is equal to 0. So the expected payoff of player 2 of playing L or playing R, given that player 1 chooses as follows, given the type he is 4 times 1 minus P. And in this way you can fill all entries of both matrices. So now we have the payoff as entries in the of the three players as entries in the payoff matrix, and we can solve for the Bayesian-Nash equilibrium. So at the top, I just repeat what's at the bottom here, and then we go to solve the best response of each of the three players. So for example, player 1 of type T is 6, given that player 2 plays L and player 1 of type T is 0 plays up, needs to decide, okay, what is optimal for me to do, up or down. Up gives me a payoff of 6, down a payoff of 2. So it's optimal for me to play up. And also here, 6 is more than 2, so it's optimal to go for up. If player 2 plays right, it's optimal for me to play down. So there's a line here. It's optimal for me to play down. So there's a line here. Similar for the player 1 of type T is 0. He compares 0 and 2. It's optimal to play down if player 2 plays L. And also here. And you can see that the entries, these two are always identical because the payoff to player 1 when he's of type T is 0 doesn't depend on what he does if he would be of the other type, because he knows that he is not of the other type. So these two entries are always identical. These two entries are always identical. Same here. And also for the player 1 type T is 6 player, the 2 6s here are always identical. These two entries, the 2s, are always identical because the payoff of player 1 when he's of type T is 6 do not depend of what he would decide if he were of the other type. And we then also need to consider what's optimal for player 2 to do, playing left or right. So player 2 will compare the 2 here to the 0 here, because that's what is optimal for me to do given the strategies of the player 1 types. Now 2 is more than 0. Here he needs to decide, okay, left gives me an expected payoff of 2p. Choosing right gives an expected payoff of 1 minus p. What is more? Now that depends on the value of p. And also here, now this one is easy. So 0 is less than 4. So given the strategies of the two player 1 types, it's optimal for player 2 to play right. And after having done this, so we can determine the Bayesian-Nash equilibrium by looking at what are the combinations of strategies that do not give any of the players an incentive to benefit by unilateral deviation. Now, one thing that we can see is that here we have all three numbers underlined. So the strategy, the combination of strategies where player 1 will play down, always, independent of his type, and player 2 will play right, that is an equilibrium. However, this is not a mixed strategy Bayesian-Nash equilibrium because player 1 will not mix. He chooses D always, and also player 2 will not mix. He plays R always. Now, player 1 type T is 6 playing down, player 1 type T is 0 playing down, and player 2 playing right. It's the only entry in the matrices where all three numbers are underlined. But there's a second case where two of them are underlined, and that's the entry that we have over here. Player 1 type T is 6 playing up, player 1 type T is 0 playing down, and player 2 playing left. Now this is a Bayesian-Nash equilibrium as long as 2p is at least equal to 1 minus p. And then we can solve for p, and we find that that holds as long as p is at least equal to 2/3. So then this is a Bayesian-Nash equilibrium as well, but we already knew that because it's exactly the solution that we found a couple of slides before. And this is a Bayesian-Nash equilibrium in pure strategies. So now we are ready to look for Bayesian-Nash strategies in, or Bayesian-Nash equilibria in mixed strategies. So let's do that. Again, these are the same matrices that we saw before, but I have made the entries corresponding to player 1 type 0 playing down. I mark them in gray to make life a little bit easier, because these are the entries that we have to focus on. Because if player 1 is of type T0, it's a dominant strategy for him to play down. So these four elements, they don't matter. So now suppose that player 1, if he's of type T is 0, he will choose D with probability 1. And suppose that when this player is of type T is 6, he will mix and he will choose up with probability Q. And player 2 will also mix and he will choose left with probability R. So then we get the following. So this is a decision variable, Q and R, and the P is given. It just determines the probability with which player 1 is of type T is 0 or T is 6. So player 1 cannot influence this probability, but this probability is something that the players can influence. Okay, so then the expected utility of player 2 of playing left is equal to, well, if he plays left, then either he ends up here or there. And this is the situation where player 1 type T is 6 plays up, which happens with probability Q. In that case, he gets the payoff of 2p. So the expected payoff is 2pq. And well, if player 1 is of type T is 6, then his payoff is equal to 0. So the expected payoff of player 2 playing L is 2 times pq. Now suppose that player 2 plays right. What is his expected payoff in that case? Well, if player 1 is of type T is 6, then he will choose up with probability Q, in which case player 2 will receive a payoff of 4 times 1 minus p. So we have this term 4q times 1 minus p. And if player 1 is of type T is 6 and plays down, which happens with probability 1 minus q, then the payoff to player 2 will be equal to 4. So the expected payoff of player 2 of playing right is, well, if we simplify, 4 minus 4pq. And of course, it's our task to solve for p and q. Now going back, we know that if player 2 mixes in equilibrium between left and right, then the expected payoff of playing left must be equal to the expected payoff of playing right. So in other words, these two, they need to be identical. So we equate and we solve and we arrive at the equation Q is 2/3 over P. And now you might think, well, okay, what did we learn? Because we have still two unknowns, Q and P. We expressed one in terms of the other, but we did not find a solution. Well, in fact, we did, because the P is given to the players. It's a variable that is known, and only the Q is a decision variable. So this shows you that if Q or if P is at least 2/3, then player 1, when he's of type T is 6, he will choose U with probability 2 over 3P. And this condition, of course, is imposed because if we take P smaller than this value, then the probability Q will exceed 1, which is not possible. So that explains this condition over here. Now for player 1, given that he's of type T is 6, we can also compute his expected utility. Now if he plays up, then if player 2 plays left, then the payoff to player 1 will be equal to 6. So this one over here. That happens with probability R, because that's the probability that player 2 will play left. And if player 2 plays right, well, then the payoff of player 1 type T is 6 will be 0. So we have no second term here. And in case he plays down, then in all instances, independent on whether player 2 plays left or right, the payoff to player 1 type TS6 will be 2. Again, if in a mixed strategy Bayesian equilibrium, the player 1 conditional being on type TS6 will mix between up and down, then in that equilibrium the expected payoff of playing each of these two actions should be the same. So we again equate and we find that R is equal to 1/3. So we now found a solution. We have a Bayesian Nash equilibrium in mixed strategies, and it's the pair of strategies where player 1, if he's of type 0, will always place down. If he's of type TS6, he will mix and he will choose up with probability 2/3 times P. And we know the value of P. And player 2, he will choose left with probability 1/3. When you do calculations like this, you can easily make a mistake. So it's always worthwhile to check whether you did everything correct. So let's check these expressions by plugging in a specific value for P, the probability that player 1 is of type TS6. So we repeat the game over here, and we found in the previous slide that we have a Bayesian Nash equilibrium in mixed strategies. And now we plug in a specific value. Take P is 3/4, which is larger than 2/3. For that value, probability Q is equal to 8/9. And then you can check that for player 2, he's indifferent between playing, given that player 1 follows his equilibrium strategy, player 2 will be indifferent between playing right or left. In both cases, his expected payoff will be 12/9. So please check that yourself. You can also check that for player 1, conditional on being type TS0 and conditional on player 2 mixing with probability 1/3, that the expected payoff of playing up is 0, which is less than the expected payoff of playing down. So indeed, player 1, if he's of type TS0, will play down for sure. It's a pure strategy. And if player 1 is of type TS6, then you can check that the expected payoff of playing up is identical to the expected payoff of playing down. And in both cases, it is equal to 2. So we find that this indeed is a Bayesian Nash equilibrium, because given what the other player does, no player has an incentive to deviate from the given strategy. And that brings us to the end of another fascinating lecture. There's one other paragraph in the book about experimental games. So experimental economics, it's also one of the fields in which I'm an active researcher. One of the things that's done in experimental economics is to bring stylized games to the experimental laboratory and to see the extent to which the equilibrium predictions of these games are followed by subjects in the lab. So how well does the theory predict the decisions that people make in the empirical practice? So examples of games that have been brought to the lab are the dictator game. Now we saw an example of that in the previous lecture when we dealt with the Andreoni-Miller experiment, the prisons game, the ultimatum game, and all these games answer the question, okay, how do real people, often they are students, but also students are real people, how do real people play games? And more of this is discussed in the minor course, Behavioral and Experimental Economics. You may have taken that course. If not, well, if you are interested in this and you have another opportunity to take that course, then I really can recommend doing that. We're at the end of this lecture. Thank you again for your attention. This is a reference to the paper with the penalty kicks. You might read up on that one as well. And I hope you had an enjoyable couple of hours, and I wish you a very nice day.